Let's start from the beginning. We all know that deep learning has become a hot branch of data science these days, which is used to solve most of the classification and even non-classification problems in machine learning. But it's good to know that deep learning itself is not a new branch of knowledge. Actually, its concept was introduced in machine learning long ago, but it was not that popular back then. But why? Because there is a fundamental problem in training the deep learning models. The problem happens during backpropagation process, and it is called vanishing gradients. When the gradient is big, the training would be fast, but the problem is when the gradient is small, which will slow down the training process. The gradient is big at the beginning of the backpropagation process, which is the last layer, and it is much smaller for the first layers, so it vanishes when we reach the first layers. First layers of the neural networks contain the fundamental features of the data. For example, in face recognition using deep networks, first layers of the DBNs contain the coarse form of the face, so the inaccurate prediction would lead to big errors. In addition, backpropagation requires labeled data, while most of the data that we deal with normally will be unlabeled. So the deep leaf networks are used to overcome the problem of backpropagation in some way. Why should we use deep leaf networks or DBNs? DBNs solve the problem with backpropagation using pre-training. Thus, we should pre-train with dataset A and fine-tune with dataset B. And in that case, weight initialization would not be random anymore. If we stick to using backpropagation and perform pre-training before that, the error would be much smaller than when the weights are selected randomly. DBNs will be considered as a stack of restricted Boltzmann machines, or RBMs. In structure, RBMs are similar to multi-layer perceptron or MLP, but in training, they are different. Each RBM helps finding the global features, while in MLP, early layers find the coarse shape and the later ones detect the details. So let's see what deep leaf networks really are. DBN is a class of deep neural networks which consists of multiple layers. They are also called generative graphical models in which the connections exist between layers and not between units in one layer. There exist both directed and undirected layers in a DBN. The hidden units inside the DBN are not connected, but the connections exist between the layers. In order to understand how a DBN works, we need to learn about two important components of the DBN: the belief network and the restricted Boltzmann machine, or the RBM. So what is a belief network or a Bayesian network? A belief network is an acyclic directed graph which consists of stochastic variables. A stochastic variable is a variable whose value depends on the outcomes of a random phenomenon. In belief networks, we have the values of some of the variables, and we would like to solve the following problems accordingly. First of all, we would like to infer the binary state, 0 or 1 state, of the unknown or unobserved variables according to the observed variables, which is called an inference problem. Secondly, we would like to adjust the interactions between the variables such that the model generates the values close to what is already observed. Now let's see what a restricted Boltzmann machine, or the RBM, is. A RBM is a shallow neural network with two layers. The layers in an RBM are fully connected. RBMs share the idea of data reconstruction in autoencoders. RBMs can be thought of as stochastic autoencoders, in which instead of deterministic functions like ReLU, it uses stochastic units with particular distribution. RBMs consist of visible units, hidden units, and a bias term which is connected to all of the visible units and all of the hidden units. The restriction is because we force the units in the same layer to be disconnected. RBMs are sometimes called two-way translators as well. since they can translate the visible units in a different representation and translate back to the visible units again. Here we are going to talk about the summary of the applications of RBMs. RBMs use unsupervised learning methods to learn patterns in the data by reconstructing the input. Some of the applications of RBMs include feature extraction, dimensionality reduction, collaborative filtering, and they also serve as the main component of the DBNs. So as you can see, they are simple, but they are pretty useful. Here you can see the simple structure of the RBM. As you can see here, they have two layers, the visible layer and the hidden layer, and they are also fully connected. The visible units are translated to the hidden units, and backward process is also possible. There is also a bias unit which is connected to all of the units, visible units and hidden units. So here's how RBMs work. Consider the inputs or the visible units as binary values, zeros or ones, and compute the activation energy as you can see here, A sub I, in which X sub j, W sub ij, and A sub I show the state of the adjacent units j in the visible layer to the hidden unit I, the weights, and the activation energy respectively. Let P sub I be equal to sigma of A sub I, where sigma of A sub I is the logistic or sigmoid function. The sigmoid function is close to 1 when the activation energy is large and positive, and it would be close to 0 if it is negative. Then the hidden unit I is on with probability P sub I, and off with probability 1 minus P sub I. Compute the following value for each edge, which is called the positive phase of edge E sub ij. Then we reconstruct the visible units in the same way by computing the activation energy for them. And then we should consider computing the negative phase as well. This is shown here as negative phase of the edge E sub I and j. The updated value for the weight is shown here. It is equal to the W sub ij plus L times the difference between the positive phase and the negative phase. And we should repeat over all training examples in one epoch, then repeat until convergence and until we have different iterations and epochs. We should note here that L is the reigning rate. Convergence will happen when the desirable number of epochs or iterations is achieved, or the error in the visible layer is less than a threshold that we have already considered. We should also note that this weight update has a name which is very famous, and it is called contrastive divergence. The benefits of the RBMs are given here. RBMs are useful since they are good in handling unlabeled data. They can also extract features from the inputs. RBMs are efficient in dimensionality reduction, and they act even better than PCA or principal component analysis. Here in this slide, the full process of the DBN is explained. This process consists of two phases: pre-training and fine-tuning. Pre-training is done using a stack of RBMs such that the model learns the features of the visible layer and the features of the features and so on. The fine-tuning phase is done using the feed-forward MLP or multi-layer perceptron or the sigmoid belief networks. For pre-training, we use iterative Gibbs sampling and greedy layer-wise learning. For fine-tuning, we can use back-propagation, which is supervised learning, or wake-sleep algorithm, which is considered as an unsupervised learning method. Here we are going to briefly explain about greedy layer-wise learning for RBMs. Stacking RBMs will help us with improving the prior of the RBM layer. The greedy layer-wise learning scheme suggests that each RBM should be trained separately starting from the bottom, and after the training of the lower RBM is done, the outputs will form the initial values for the next RBM's inputs, and the next training starts. This procedure is done until we reach the convergence criteria for the RBMs. Fine-tuning is used for training the sigmoid belief networks. If we use backpropagation, we need to have labels for the supervised learning in order to find the best weights. Since we want to work with unlabeled data, unsupervised learning, we need to apply wake-sleep algorithm. In the wake-sleep algorithm, they consider two different sets of weights, such that one of these sets of weights is according to a wrong assumption. Finally, in this slide, you can see the simple structure of the DBN, which consists of both sigmoid belief layers together with a stack of restricted Boltzmann machine.